Department of Collegiate Education, Digital Learning. This is a video on electricity and magnetism, which is a part of Unit 1 of BSc Physics, 3rd semester. The video is presented by Savita S. So the contents of this video are Norton's theorem statement, procedure to analyze Norton's network, equivalent circuit, example problem on Norton theorem, statement of reciprocity theorem, solved example. Norton's theorem statement. The current in a load resistance RL connected to two output terminals of a network consisting of one or more sources and resistances is the same as if the load resistance were connected to a current source IN in parallel with a resistance RN. So suppose we have a two-terminal circuit here. A complex circuit is there which is connected to the load. Then this two-terminal linear circuit can be replaced by a single source, current source of current value IN and a resistance RN connected in parallel with the source. So this current source and a resistance connected in parallel with the current source is equivalent to this two-terminal linear circuit. So this equivalent circuit is now connected to the load. IN is called as the Norton's current and RN is the Norton's resistance. So this equivalent circuit is called as the Norton circuit. So just like Thevenin circuit, where we simplify the circuit by using Thevenin's voltage and Thevenin's resistance, using Norton's theorem we are simplifying the complex network by having a current source and a resistance in parallel with the current source. We'll see how we can Nortonize a circuit. So to find the current, suppose we have a complicated linear circuit. So to find IN, so what we have to do is short the output terminal after disconnecting the load resistance. So this is a complicated linear circuit which is connected to the load resistance RL. So we are interested in finding out load current IL. So first step is remove the load and short A and B. Short means just connect them by a wire of negligible resistance. Remove the load and short A and B. Then calculate the short circuit current IN. This short circuit current is called as the Norton's current. Second step is, again we will take the complicated network, replace all sources by their internal resistances and then open the output terminals. All voltage sources are short circuited and all current sources are open circuited. So open the output terminals. Earlier we had shorted it. Now open the output terminals. Replace all voltage sources by their internal resistance. Now looking back at the circuit, find the effective resistance. That effective resistance is called as Norton's resistance. So we have found IN and RN, Norton's current and Norton resistance. Now replace the complex network by current source of value equal to IN and a resistance in parallel with the current source of value equal to RN. So this equivalent circuit is called as Norton's equivalent circuit. So instead of the complex network, we can use the simplified Norton's equivalent circuit, which is again connected back to the load. So this circuit is similar to a complex circuit. Using this simplified circuit, we can find out the load current. So to find the load current, we use this formula, branch current formula. So load current is nothing but main current, that is current source IN into resistance of the other branch RN divided by sum of the resistance RN plus RL. So main current when it comes here gets divided into two branches. One through RN, another through RL. So current through RL is called as the load current. Load current is given by main current IN into resistance of the other branch, that is RN, into sum of the resistance RN plus RL. So this is how we find the load current. Whatever load current we get from this will be same as what we get from the complex network. So we'll see how exactly this can be done by solving a problem. Suppose we have a complex network here wherein we have a source of 12 volts and 3 resistances, 1 kilo ohm, 2 kilo ohm, 100 ohms and 1 kilo ohm. Now first we have to Nortonize this circuit. Then we can find out the load current easily. So just like how we Thevenize a circuit, we can Nortonize a circuit. After simplifying the circuit, we'll have a single current source and a single resistance. Instead of 3 resistances, we have a single resistance. Instead of the voltage source, we have the current source. And the load will remain as it is because we are interested in finding out the load current. Now to Nortonize this circuit, what we have to do is first find the Norton resistance. Norton resistance. To find Norton resistance, remove the load resistance, replace the battery by its internal resistance and find the effective resistance of the circuit. Remove the battery, remove the load, replace the battery by its internal resistance and find the effective resistance by looking back at the circuit from the open end. Open this 1K, source and load removed. Remove the source and remove the load and replace the source by its internal resistance. Now what is the effective resistance means? If we look at the circuit from the output end, then 1K and 2K are in parallel because this is removed now. 1K and 2K will be in parallel, that is in series with 100 ohms. So 1K, 2K are in parallel. 1000 into 2000 divided by 2000 plus 1000. This entire combination, parallel combination, is in series with 100 ohms. So the effective resistance will be 767 ohms. So this is called as the Norton's resistance. That needs to be connected in the second part of the circuit. Now to find Norton current, we will first find the main current. Main current is given by E by R, EMF divided by resistance, by removing the load and short circuiting the output terminal. So for the second part, we should replace the battery. Battery should be replaced back to its original position. Remove the load and short the output terminals. So suppose these are the two ends. This end needs to be shorted to this. So EMF is now 12 volts. Our resistance is now 100 and 2K are in parallel. This is removed. 1K is removed. These two ends are shorted. So this end and this end are similar. So 100 and 2K are in parallel. That parallel combination is in series with 1K. So 1K plus 100 into 2000 divided by 100 plus 2000 is the effective resistance of the circuit. So 12 divided by the effective resistance will give you the main current, 10.9 milliamps. So Norton's current, short circuit current, is given by main current into. So this main current, when it reaches this point, gets divided into two branches. This branch and this branch. Remember that the load is removed now. So we have two branches. One having a resistance of 2K. Another is having a resistance of 100 ohms. This 1K is removed now. So 1000 plus parallel combination of 100 and 2K. 100 into 2K parallel combination is this. So total current. The Norton current is given by total current into resistance of the other branch 2K divided by sum of the resistance 2K and 100. So this is removed. So sum of the resistance is 2K plus 100, which is equal to 10.43. Now in the simplified circuit, we have Norton's current source and Norton's resistance. So load current is given by main current, Norton's current, into resistance of the other branch. This main current, when it comes here, gets divided into two branches. So we'll use branch current formula. Main current into resistance of the other branch, Norton's resistance, divided by sum of the resistance, 1K plus 767. This is equal to 4.5 milliamps. So that is how we find the load current. So from the second simplified circuit, in a simplified circuit we have current source, Norton's resistance and load resistance. So when this current from the current source reaches this point, it gets divided into two branches. So we use the branch current formula. Main current, that is IN, into resistance of the other branch, RN, divided by sum of the resistance. Sum of the resistance is Rn plus 1K. So that is how we calculate the load current. So next is part of the network theorem is reciprocity theorem. So the theorem states that when the voltage and current source in any network are interchanged, the magnitude of current and voltage flowing in the circuit remains unaltered. So this theorem is applicable to linear bilateral networks only. Suppose we have a circuit here where we have a voltage source and a current source. Suppose if we interchange the two. So in this branch we have current source. So wherever voltage source is there, there you put the current source, and wherever current source is there, if you put the voltage source, if the two sources are interchanged, the magnitude of current and voltage flowing in the circuit remains unaltered. The magnitude of current and voltage in the circuit remains unaltered. That is what the theorem says. So we will see whether it is true or not by solving a numerical problem. So we have a circuit here where we have a battery of 1 volt and 3 resistances, 1 ohm, 8 ohm and 5 ohm, and there is another resistance 3 ohm. So now this is main current is I, gets divided into two branches. I naught is a branch current. Now we will retain the resistances in their places itself, 1 ohm, 8 ohm, 5 ohm and 3 ohm as it is. We will change the position of the battery and the branch current. So battery position is now changed. Wherever the branch current was there, I naught, there the battery is placed, and wherever the battery was there, there I naught branch current is taken. So in this case, we'll see whether there is any change in the value of current I naught, branch current. We'll calculate what is I naught in this case, what is I naught in this case, and we'll see whether they are similar or not. If they are similar in both the cases, then it is proving reciprocity theorem. So first we'll concentrate on the first circuit, figure 1. So the effective resistance of figure 1, first figure, is effective resistance is, so main current is getting divided into two branches. So 5 and 3 are in series, that is 8 ohms. This 8 ohm is in parallel with 8 ohm. 8 and 8 are in parallel. This parallel combination is in series with 1 ohm. So 1 plus 8 and 8 are in parallel. 5 and 3 are in series. So 5 plus 3 is 8. This 8 and this 8 are in parallel combination because current is dividing. So the entire thing is in series with 1 ohm. So the effective resistance is 5 ohm. So main current I is 1 volt, battery voltage is 1 volt divided by effective resistance, that is 0.2 ohms, 0.2 amps. So branch current is I naught. Main current we know what is I. Now we'll find out what is the branch current. To find the branch current we use branch current formula, main current into resistance of the other branch divided by sum of the resistances. So there are two branches here, 8 ohms and 5 plus 3 is also 8 ohms. Both are having same resistances. So branch current I naught equal to main current into resistance of the other branch divided by sum of the resistance is 0.1 amps. So I naught in the first circuit is 0.1 amps. Now after interchanging the branch current and the EMF, like shown in the figure 2. So we'll find the effective resistance of the figure 2. So in the figure 2, the main current is flowing like this. So I naught is the branch current. There is another branch current here also. So what is the effective resistance means? In this case, 1 and 8 are in parallel. 1 ohm and 8 ohms are in parallel. That parallel combination is in series with 5 and 3. 5 plus 3 is 8 ohm. So this parallel combination is in series with 8 ohm. So that will be 8.9 ohms is the effective resistance. So the main current is given by battery voltage, that is 1 volt divided by effective resistance 8.9, which is equal to 0.11 amps. So branch current is equal to Branch current is what? Main current into resistance of the other branch divided by sum of the resistance, which is again we are getting it as 0.1 amps. So there is no change in branch current if we interchange the source and the branch current. So that is what the reciprocity theorem says. So these are some of the references that the students can use for better understanding of the topic. Thank you.